Okay, after the general introduction on how to do perturbation theory from the previous session, in this session we actually do it. We actually do the more detailed theory. It's not too difficult. It just involves writing down power expansions of the eigenfunctions, the perturbed eigenfunctions, the eigenfunctions that result from adding an extra term to the Hamiltonian, and similarly with the eigenenergies, the eigenvalues, because we're talking about energy, right? The Hamiltonian is the energy operator. So now, at the end of the previous session, we wrote down our first perturbed thing of the three things: the operator, in other words the Hamiltonian, the eigenfunctions, and the eigenvalues, in other words the allowed energies. Now the perturbed Hamiltonian, so just call it H, or H hat. So H hat would be equal to H hat naught, H0, that's your basic Hamiltonian. That's the Hamiltonian of the system, hopefully, that has exact solutions, because that makes life easier. If you can perturb a system or Hamiltonian that has exact solutions, makes life a lot easier in calculations. So H hat equals H naught hat plus lambda H dashed hat. Right? And the H dashed, that's the perturbing term, that's the extra term you add to the Hamiltonian, to your H0 hat. Right? Now similarly with the eigenvalues and the eigenfunctions, okay, so so here is your corrected, your perturbed. It's the eigenvalues, the eigenenergies that result from adding the extra term, the small correcting term if you like, to the Hamiltonian. And you assume it's of this form. So it's just a power expansion in terms of lambdas, right? Lambda squared, lambda cubed, dot, 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 right? And so this is the eigenenergy. These are the eigenenergies, n, for the unperturbed Hamiltonian, without the H dashed added, right? So that they would be your eigenvalues. And when you do add the perturbing term, the extra term, to the Hamiltonian, then your eigenvalues will change, and the values, the numerical values for these energies, will be this. And now this is an assumption, it's just part of the theory of perturbation theory, is that the corrections, the changes, if you like, to the the basic eigenenergies, this one, you can write in the form of a power expansion in terms of lambda. And this lambda is just a constant, assumed to be between 0 and 1. Okay, in terms of power expansion. So this E1 here, that's the energy correction to so-called first order. So it's this E1 here then. That's your, quote, first order eigenvalue correction when you add the extra term to the Hamiltonian. Right? And similarly, this is the second order correction because it's the coefficient of lambda squared, and so on. Right? And a similar logic to the eigenfunctions. Now, these are the eigenfunctions when there is no perturbing added term to the Hamiltonian. These would be your eigenfunctions. Okay? And then you do add the perturbing term, and so your eigenfunctions will change. There's solutions. The eigenstates, they're the solutions here for the system that does have the extra term added to the Hamiltonian. And it too, you assume, can be expanded in terms of the basic part, and hopefully these solutions here are exactly solved, and so it makes life easier for calculations. And these terms are the corrections. They change these basic eigenfunctions into the eigenfunctions that correspond to the perturbed Hamiltonian. So the H0 hat plus H hat dashed, right? The dashed is the H dashed is the perturbing term that you add to the Hamiltonian. Right? Now these i's here, like for example here, 1, 2, how can I put this? In a sense, I mean, they're just coefficients of the lambdas. That's a sort of trivial way of looking at it. But in the results that we get, that you'll see in the next few session or two, these results here do not involve the lambda, but we just use the lambdas to derive formula for this is a kind of correction term, because this will be different from this. These are the eigenfunctions for when your Hamiltonian does have the extra term. These are the eigenfunctions for the Hamiltonian, just the basic Hamiltonian, that does not have the added perturbing term in the Hamiltonian. Right? So these are correcting. These are additional changes. These terms here to this to give you this. All right. Okay. So we assume that the new, the modified, the perturbed, if you like, eigenvalues take this form. We assume the eigen states, the eigenfunctions, take this form. And remember, these are the eigenenergies for the perturbed Hamiltonian, the one with the added Hamiltonian term. These are the eigenfunctions for that perturbed Hamiltonian, right? So here's now your eigenequation for your perturbed system, right? Your UN here is not this one, it's this one, right? And your En now are not the eigenvalues of the unperturbed system. These Ens are this, okay? And your H now is your perturbed Hamiltonian. So it's H0 hat plus lambda H hat dashed, right? So you can plug in this formula here. You can plug in all this here, and for H hat here, you plug in H0 hat plus lambda H hat dashed, right? The perturbing term in the Hamiltonian. Right? So you plug in all those three things into this equation. Now you put it all on the left-hand side. Usually an eigenequation is operator eigenfunction equals eigenvalue eigenfunction. That's the usual way to present it. But here we've just taken the right-hand side over, it's minus. And the reason we do that is because then the right-hand side becomes 0. And if you then plug in all these terms here and all these terms here, and the modified H, H0 hat plus lambda H hat dashed, you will get a fairly involved power series in terms of lambda. Some coefficient lambda plus some other coefficient lambda squared plus some other coefficient lambda cubed, all on the left-hand side, and all that power series in terms of lambda equals 0. So that means now lambda you can look on it as a kind of variable, just somewhere between. Well, you fix it, but you could fix it in any value between 0 and 1. Okay. So that means the coefficients of that of each power of lambda, lambda squared, lambda cubed, dot dot dot, all those coefficients, because of this eigenequation, all those coefficients have to be 0. Okay? And that's the key to perturbation theory. Because those coefficients all have to be 0, you can derive things. You can get interesting